Welcome to another tech tip. Today the focus is on total dynamic head. The days of close is good enough is gone for sizing. From residential applications, irrigation projects, and more. One driver of this is variable speed drives and broader range of flow in the home. For example, a home with a high flow shower. Pumps cannot create water, but they also may not to be able to meet all the demands of the home even with a drive. So, with that let us begin. So why is total dynamic head so important? Well, first for sizing of course. Second to use sizing programs that can show multiple condition, which is handy for understanding how the VFD will run in the system. Last is to better troubleshoot the system. So, what is total dynamic head? As you see here, it is friction loss, depth to water, system pressure and elevations. Now it is also important to understand as a pump professional sizing a pump, our job is done at the pressure tank. We do not do the friction loss calculation for the home itself, but work with the property owner or plumber, whoever is requesting the service, to ensure you understand the need. Now let us further dive into the process. A good starting point is the depth to water, both standing and to what depth the water will drop to when pumping. Sometimes this is called the pumping level or working level, to name a few. Who determines this? The well when drilled is tested by a variety of methods we do not need to cover here. It is also a good idea to retest the well when changing out the pump to ensure that the well production has not changed. A question often asked is, do you use the full drawdown even if you are using a fraction of the production? And I would answer yes. Always plan for worst case scenario. You never know what could change in the well condition. Remember, pumps move water but cannot create water. Calculate using the full drawdown. Next is the friction loss that will reduce the pressure in the system when the water is running. Some might argue that I should have started with the friction loss calculations, as they are often overlooked or forgotten. But here we are now, so let's dive in. To move water costs the system pressure. The more water demanded, the more the loss. Now if you are intimidated by math, do not worry, the heavy work has been done and charts created to streamline the process. What pipes do we have to calculate the loss in? Well, first, where is the job done for a pump professional? The answer, easy, the pressure tank. So, any pipe from the tank to the wellhead and down to the pump set. Even if a portion is underwater, we still calculate down to the pump set, as the water is moving faster than nature intended through the entirety of the piping. So, let's look at the charts. Note, we are not calculating friction loss now. We will do so later in the example. Right now, I wish to share a friction loss chart. This one focuses on fittings. The key about fittings is that rather than create a chart reflecting all the flows, this chart simply converts the fitting into an equivalent length of straight pipe to be added to the straight pipe calculation. One question is often, what about a pitless adapter? If you cannot find this information from the manufacturer, it would be safe to call it a 90-degree elbow. To calculate the fittings loss, count each type and with the chart convert the fittings into equivalent straight pipe and add these totals to the actual straight pipe. Once the fittings are converted, you need to add the total of straight pipe in the system. Using this chart, you will see it is organized by diameter of pipe, type or construction material of the pipe, and flow. And yes, this is a quick overview. We will step through some calculations in the example we will work on later in the presentation. If you want a more detailed explanation of the friction loss calculations, you can find more detail in one of our other online courses. Next item to consider is the elevation of the wellhead to the point of usage, the pressure tank. Years back this could have been difficult to measure. Now, there is an app for that. Using a cell phone, often this can easily be measured. It could be positive or negative. Meaning if the wellhead is 25 feet above the tank, we would then subtract the elevation in the calculation. In most cases the wellhead will be below the point of usage, and we will then add the elevation to the calculations. System pressure desired. There are a few schools of thought on this one. The current, traditional way is based on across the line, starting with a pressure switch typically. The method is to average the pressure, so a 30-50 switch would average to 40 and we would convert that into feet of head by multiplying by 2.31. Round it up to 93. Now that being said, does a variable speed drive work on that big a pressure swing? Typically, not, and wanting to sell a variable speed drive, I would calculate the high pressure desired. Again, converting to feet of head. So that was a lot in a short amount of time. So let us walk through the calculations. We have a site with a 6-inch well. Standing water is 150 feet. Drawdown after testing is 75 feet. The well depth is 300 feet. This is important because anytime we are working on an example submersible pump set, I always state the pump will be set 15 feet off the bottom. This is only done to ensure we all get the same numbers in the end. This is not an industry standard or a recommendation. So, knowing this, we know that the pump set is 285 feet. We see a 75-foot run of 1.5-inch pipe buried already. In the next column we see there is an elevation of 25 feet. The system pressure is a 30-50 pressure switch, and the fixture count is 20. But wait, there is an irrigation system that requires 45 pounds of pressure and 15 gallons of water per minute. Finally, we see the power available is 230 volts single phase. Starting from the top, how many gallons does the home require? Now yes, the primary limiter is the well. If the well only produces 12 gallons per minute, that is the limit. For class, it is always assumed that the well production can meet the need. So, a traditional method of determining the system demand is to count the points of water usage and total them up. Then multiply this number by 1 gallon per fixture. Doing this, we determine the system needs 20 gallons per minute. Next, select a size for the 285 feet pipe set. Knowing that we have 75 feet of horizontal pipe at 1.5 inch, why do we not make the math easy and make the drop pipe the same? Next, we need to determine the friction loss per 100 feet of run for the 1.5 inch pipe. Rather than go into the chart reading exercise, can you trust me? I looked it up and it was 2.83 feet per 100 feet. Now we total up the pipe run. Quick note: to make this an easy example, I will round numbers rather than calculate each fittings in the system, as usually there are only a few. From the example, the pipe set is 285 feet of pipe plus the 75 feet of horizontal run. This gives us a total pump run of 360 feet. Continuing, we need to calculate the friction loss. So, I know the friction loss chart is calculated for 100 foot lengths. I have 360 feet of pipe, so I divide this by 100 and get 3.6 units of pipe. Now, if you are getting a bit lost on the friction loss calculations, that is okay, we have other modules dedicated to the subject. Today the focus in on what goes into total dynamic head. From the chart, as I said before, I found the friction loss to be 2.83 feet per 100 foot lengths. Doing the math, I calculated the losses to be 10.19 feet of head. I will round this up to 11. Why did I round? Well, one reason is to try to cover the fittings I have not addressed in the system. Second reason is I am not there to inspect the actual system, so I am building a safety margin into the numbers. Now we have the friction losses, let's calculate the rest. We know the water sits at 150 feet, add to that the 75 feet of drawdown, and the 25 feet of elevation. This is the pumping level. Next, we add the average pressure in feet of head. Or 40 times 2.31 rounded up is 93. Totaling these numbers, we get 354 feet of total dynamic head. Looking at a curve, we snap two lines. The vertical blue line is the 20 gallons we need. The green horizontal line is the total dynamic head as best as I could draw it. And you see we are right in the middle of the 2-horse curve and the 3-horse curve. First question is, what horsepower do we use? Of course, the 3-horse. Now here is the real question. Assuming the tank is sized properly, where will the pump really be running? Follow the green line to the right and you will see where it crosses the 3-horse curve. It looks like about 23 or 24 gallons per minute on average. Why is this important? It can change the tank sizing. But again, this is a topic for another module. Where this can really impact a system is irrigation. So why is total dynamic head important? A great reason is it opens the ability to use a sizing program. Now here the curve looks familiar, however you will notice it shows only the 3-horse curve. And again, looking at the blue horizontal curve shows the pump will be running about 23 or so gallons per minute. So is there a better way to size a pump? No, not really, but there is a better way to run the pump. And that would be with a variable speed drive. Running across the line with a pressure switch, the pump runs full speed and this causes numerous issues. Now quick, what is the red line? And where does it come into play? This is the minimal sustainable constant flow. It is more important when running a variable speed drive, and we will discuss this later. Simply put, do not run to the far left. You can lose proper lubrication of the pump, cooling of the motor, and have hot water cavitation issues. In short, stay in the middle of the curve. It is also important to keep in mind that as you go to the right of the curve, the amps increase. The farther right you go, the higher the amps. And running on the right for a period of time will create excess heat in the motor and can cause premature motor failure. So again, keep to the middle of the curve. Understanding total dynamic head allows you to explore the system through the lens of a variable speed drive. Here I left the primary at a static or constant RPM to show across the line running of the pump. Next you see various running conditions. A single shower head running 3.5 gallons per minute. A washing machine running 10 gallons per minute. All three showers running a combined 10.5 gallons per minute. And finally, I took the time to recalculate the total dynamic head for the irrigation system, making the curve green to show up better. Recalculating the system, one thing that pops up is the near miss of the single shower at 3.5 gallons per minute. Why is this? Here is the curve the data produced. And now we see the single shower is below the minimal constant sustainable flow. Now is this a concern? Yes, with a small tank it very well could be. This is why tank sizing is critical. But also, not how the horsepower consumption varies depending on the gallons per minute? How do you show the impact of a variable speed drive? You must understand total dynamic head. One final note on reading a chart. Remember, if you calculate total dynamic head, system pressure is included in that calculation, thus as seen here, size using zero system pressure. If you make the mistake of adding an additional system pressure, you may oversize the motor and pump for the system. Wow, that was a lot. The key is to know what total dynamic head is and how to calculate it, including friction losses, pumping level including elevation, and system pressure. Once you have this number, you can size a pump far more accurately. Thank you for joining us today and looking forward to speaking with you next tech tip.